Alright, so let's look at today's Leetcoding challenge question. It's called first unique number. So you have a queue of integers. You need to retrieve the first unique integers in the queue. So it's a data structure design question. I think I guess the underlying data structure is queue, and that queue obviously would support add numbers to the queue, and it will also support this show first unique method, which will return the value of the first unique integer. If there is no unique number on the queue, we return -1. And the initializer is just calling this add operators for all the numbers in the initial list or array. And I guess the goal is to make this show first unique very fast. It's a strange that this queue don't need to support pop, so it's kind of strange. So let's look at the example. We have we constructed a queue with 2, 3, 5. That's going to be the numbers on the queue. So if we ask for the first unique, we'll return 2. That's the first unique number there. Every number at this point is unique. Then we add 5, so that 5 is no longer a unique number, but that doesn't change the fact that the first unique is still 2. We add 2, that really changed things. The 2 is no longer the first unique. The only unique now is 3. And then we add 3. There's nothing on the queue that's unique. We return -1. So just based on this very first example, we can see that whenever we add the number twice for the second time onto the queue, since that the queue is just the one only in, no out, it's effectively not there for the purpose of show first unique. So we're just going to have a set to keep track of the number that we see. If that number we see for the second time, we don't need to put that number on the queue. And also we can actually just remove whatever the first occurrence of the number from the queue. And on the queue itself, it just needs to be ordered so that the first unique is always going to be the first element on the queue. So so that gives us a pretty straightforward solution to satisfy this. When we get pop, if we are required to write pop, it will be more complicated. Yeah, so I guess for the language of my choice, Python, I can just use a dictionary. The key is going to be ordered, so I'm just going to use that dictionary as the to order the elements onto the in the queue. And also the key value, I can access values on the queue in constant time just by using the key. And deletion is also in constant because it's like a doubly linked list. So we extract a node out, we just establish the other link there. So that gives us a combination of ordered dictionary or linked hash map with a set to keep track of the elements we have seen. That two data structure combined can support add in constant time and show in constant time. So that's pretty much it. Let's code this up. So for this, it's going to be very easy. The key, we're just going to return the first key on the queue here. And I put a default -1. So if the queue is empty, we just return empty -1. For add, so there is a two condition here. If the value it's already in the scene, so it's at least the second time that we see this value. What we would do is to try to delete that number from the queue. If it's not there, we're just return an empty value, whatever, it could be anything, -1. Otherwise, we would update otherwise it will be the first time we see this number. So we definitely want on queue the number onto the queue. Also, we remember this value. So remember, this value is just setting a random key value pair for it. So it's pretty much it. This value doesn't. All we relying on this dictionary is use it as a random accessible, constant accessible double linked list. The value doesn't matter. So that's pretty much it. Let's see. 2, 2, 3, -1. That's aligned with this example. Okay, so let's submit. It's working. So that's the quick, dirty solution for if we don't support the pop operator. So let's think about what if that we actually want to support a pop operation, and how does that change things? So let's say that we have a queue that looks like something like 2, 3, 3, 2, 5. So the first unique is here, and when we actually do a pop, it will become 3, 3, 2, 5. Then we have to go back and scan again on the queue to find the first unique. For that reason, we can't really just popping values out of the queue. We might want to actually just use a regular queue as a queue, but be able to find that location. Sorry, shift this. Find that location very quickly. So what's gonna be the since that how can we do that? How can we do that? Okay, so I guess one way that we can do is to maintain the previous and next kind of relationship between the values on the queue. So let me make it a little bit more concrete. So obviously, as a doubly linked list, the values here are looking like this, and beyond that, I think what can be useful is that if we maintain a relationship like this, let's call this the next pointer. For every integer node, a node representing the integer on the queue, it has a next pointer pointed to the next available next value on the queue, and it also has a the node also have a pre pointer that points to the previous occurrence of the same value in the queue, so that when we are scanning through this array, so that when we delete when we pop this 2, let's say that the first unique is here. So when we actually pop this 2, we will look into the node here. Since this one has no next pointer, and it's before 5, this deletion, this pop will make to the first unique. There can be multiple different nodes here in between 2 and 5, but after that pop, we need to move the first unique back to this 2 here, and we want to if we have a ways of doing that, we will be first is that this next pointer and the previous pointer can help us to identify the necessary change in constant time. When we pop it off, we just check the dot next is none, so that we know the second occurrence of 2 here would become the first unique when we pop 2. And we will have a way to actually move the first unique location back to here. Okay, I see. So I think we're gonna have a node object. So you will have the value. You will have a sequence number, which is the it is the n's number that's being added to the queue. So that for every node on the queue we have a timestamp. But this integer number, will also help us to access the node in the queue in constant time. We can do a simple calculation. When we look at this node's sequence number, and we know that the first node's sequence number actually on the queue, we can just do a subtraction, and that gives us an index accessor for the numbers on this queue. So this will be the way to do it. So for this to work, this queue has to also have the index accessible method. In Python, I think this just regular list or array. They are pretty much it, working like this. So we're gonna have 2 pointers, which is pre and next. And in our add and pop operations, we're gonna maintain this as 2 pointers. And the sequence number is just increment every time that we add a new node to the queue. Yeah, that's pretty much the design. I think the show first unique is going to be a little bit slower when we add a new node that's invalidating that, because we have to update the first unique pointers now. It's going to be something we also maintain. It's no longer free as what we have in the simple solution without any pop operation support. So yeah, let's finish the coding. So what do we do? So the queue now is it should be a deck, and we're gonna get rid of that, and just call it scene, I guess. Now it's still a dictionary. Yeah, well, I'm not sure why I removed it. Okay, it's a dictionary now, and we have a current pointer, which is pointing to the current candidate for the first unique. We're gonna advance it when we add a new node and invalidate the current unique one, and so initially this is 0, and the sequence number initially is also 0. So for adding nodes, how does the code look like? So we're gonna create a physical node here. The 2 pointers in the beginning is none, and we're gonna increment the sequence number by 1. And what do we do? Obviously, since that we insert this new node onto the queue, we're gonna update this to always keep track of the very last occurrence of the node on the queue. Value. And we're gonna establish the link here, which is if we have a previous node in the queue, we're gonna have this node, this new node, this previous pointer pointing to that. So this is to establish the two-way reference links, and this is put the node to the end of the queue, and we increment this sequence number. That's the add operation. It's still constant, constant in time. Let's do the pop. So we will actually physically pop the node off the queue. After we pop, what we will do? So if this node is the last node on the, if the node is the only node with that value on the queue, we should remove it from the hash map, because we no longer need to either access it or establish links. That's determined by so if this is referencing to the node, we will just remove it. And then is this case here. If we actually remove a node, that will cause the other copy, the other instance of the value in the queue to become the first unique, and that node just so happens to be smaller than the current unique. You know, in terms of ordering, then we want to move that current pointer to this location. So that's determined by if the pop node has a next pointer. Obviously, the first thing, obviously before we actually do this rewiring, we are gonna drop this previous pointer. So this is telling us that after the pop, the node will that node's value will become the become the unique one, and what we need to do is to let's call this location. Actually, this location is gonna pointing to is the one that we access the first unique value on the queue. It's gonna be so since that we decrement, we remove one node from the queue. If for any kind of case, we have to shift this to the left by one, the index accessor by one. If we actually need to move it, it could be go even further towards the left. So that's taking the minimum between this value, and the new calculated value, which is actually just to be the difference between the next copy of the value's sequence number and the popped node's sequence number. So this abstraction is telling us where the second appearance of the node before occurrence would be after the removal of that node. So that's the pop. It's also a constant time operation, and if we actually need to move the valid first unique value pointer location indexer in the, we'll actually just directly transport it over there. So if we call pop and then call show first unique, the time will be in constant time. So let's code the very last thing, the first show first unique. So while we still reach the end of the queue, we should search for the first unique value. That's when the current one is not. So we can access the node by using this location. And the way to verify whether this value is the unique one is to check whether that node has no pre and no next. If it has either of those, that means there is a duplicated value in the queue for that value. So the condition is if it has either of these two pointers, we would just ignore, we would just advance the location towards the right by 1. Otherwise, we would just return this node's value, because this node is the first unique value. So if we reach the end of the queue and still couldn't find a unique value, we return -1. Let me quickly check. Let's comment this out. This kind of design stuff. So we have object node, which is the value, sequence number, pre, and next, which is helping us to navigate through the multiple copies of the nodes on the queue. Also to help us to determine whether this node value is going to be unique on the queue or not. We have a queue and scene dictionary, which help us to access nodes on the queue in constant time. And so this is a scanning through the linked list to try to find the next unique value. This is the addition. So we put a node onto at the end of the queue, and if we have a node on the queue, we will establish the pre-reference. We'll also we establish the two-way reference here, and update the location of the of the latest node on the queue. So when we pop the node, we pop the very first node on the queue, and if it's the only node, we just remove it from the hash map, because we no longer need to access that. And then we check whether this removal would cause the we remove the link between the next occurrence of the node on the queue with this one, because this one is being popped. So we set this pre-reference to be none, and if that removal, the pop, will cause the second occurrence of the value to become the first unique, it will try to advance the location pointer to that location by doing this calculation. Yeah, it seems right to me. Let's the test case won't test this because it doesn't support the pop. But at least I think the add is can be shown here. It's working. But the pop, I guess you can reason through that it should work. I guess for this, the time for this is no longer constant. After the pop, the show first unique is gonna be constant. When we add a value that's a unique number, or as long as it's not this current unique one, when we do the add, after that addition and we call the first unique, it's still going to be constant. Otherwise, we will actually just scanning through the linked list towards right, traversal through, and try to find the first unique value. I think if I know how to do amortized analysis, I think that might be constant in that respect. But I guess the worst case is in one of the operation, it can potentially just traversal through all the nodes on the queue. That's the worst case. But on average, I guess in amortized kind of situation, it will be constant. Yeah, so that's the solution. That's my solution with the support for pop. So the trick is to the design is to have the nodes on the queue that have pointing to the next and the previous, so that we can move this first unique location very quickly back to the prior locations when we do pop and make that value become the first unique. So it will go back to that location in constant time. Alright, so that's it for today.